So my name is Artem, and today I would like to tell you about how to crawl 100 gigabyte per day with Go. And this is basically a toy project that I've been working on recently. And here are a few numbers to get your curiosity and attention. So it's not 100 gigabytes; it's maybe a bit more nowadays. And there are a few things happening there. But in one sentence, what I'm doing, I crawl the internet and other open data sources in hope to get the data and build meaning from that data, build knowledge from that data. But let's talk first about computer science. I'm a software engineer. I've been doing software engineering for 15 years, and computer science was never a big part of my life. Obviously, everything that I use is kind of based on computer science, but I'm not a scientist, and my daily life is like implementing certain business cases for the client and business tasks or integrating some legacy software, legacy services, and computer science is not exactly clear how it can help me. But it got changed maybe 3 years ago when I don't know how, but I accidentally found one paper. The paper itself was published in 1998, so more than 20 years old. And while I was reading that, I was so much impressed by the paper itself. And maybe you recall some of those names. You've seen it maybe somewhere. And when I was reading that, I realized that I wanted to build the same. I wanted to build search engine. And back in the time, it was a kind of crazy idea. It wasn't related to my work. It wasn't related to I didn't know anything about computer science, all this stuff behind search engine. And I didn't even know if it's possible or not. And after 3 years of heavy research and multiple attempts and hundreds of hours spent on that topic, I still have no idea. But that kind of, even though at the end I accomplished basically nothing, I still enjoyed the journey itself. It's kind of become my hobby, my maybe passion to try to build search engine. But maybe some time ago I realized that the thing that happened with me is that I was reading this paper and it inspired me to try the new field that I didn't even consider. I didn't even know that it exists. I mean, the field about data mining, about information retrieval, all those things. And it's inspired me. And I was thinking that, can I actually experience it the same? Can I build something that could inspire me, maybe someone else, through computer science papers? But like it's not impossible already, the top cherry on the top that I have no knowledge about computer science. I'm not PhD. I don't even remember anything from university. So kind of least qualified to implement this task. And given the two random papers, I have no knowledge how to even compare which one is better. I'm not a domain expert. How to solve it? Basically, we can get back to the Google. What Breen and Page did in 1998, they invented this algorithm PageRank, but Google wasn't the first search engine back in the time. Maybe AltaVista, someone remembers. But what Google did differently with PageRank, they didn't analyze only the page itself. If you go to apple.com, well, for you it's obvious that it's about apple.com, but for computers it's quite difficult. They can take some keywords from the page, but nothing else. But what Google started to use, it's rather than analyzing the page itself, it's actually analyze all the links to that site, all the millions of pages that exist in internet. They analyze that all those pages are about Apple, and it has a reference to Apple. So most probably the most relevant response for the Apple query is apple.com. So rather than try to use some AI to understand, most probably now it uses AI, but still, rather than trying to understand the page itself, they used existing knowledge which is spread across the internet to find out what is that page. And we can try to use the same. What if we will just take two random computer science papers, and one is currently being discussed by 1,000 people. Computer scientists, computer engineers, they all discuss in that paper. And the second paper is currently being discussed by one guy with himself. Which one is better for our purposes? Well, obviously the first one, because most probably that first paper has some breakthrough, something that wasn't possible before, something that maybe mankind didn't know how to do, but now it knows. Or maybe it could be just a very funny paper. It also exists. So, and that's how I decided to solve it. So I monitored Twitter for all the messages that looks like a paper discussion. So I cannot find like computer science paper. No one is using those words. And so there are a lot of filters. And then I try to download all the links. I try to understand which links, which papers about computer science, which are not. There's quite a lot of false positives. Then aggregate filters, do a lot of post-processing. You may notice that we dramatically simplified things. At the beginning it was about inspiration, about finding new ideas, but now it's silly Twitter application that get the data, put in a database, return. So, and how is even Twitter relevant across computer scientists, across PhD students, across computer science professors? Most probably it's not very relevant. But this is the first problem, first open problem, that such task cannot be solved completely. I've been doing different ordering system, ecom, and if I'm doing some ordering system, once it's done, it works. It works all the time, and if it doesn't work, it's unexpected. While with search engine, recommendation engine, all those kind of system, which is this kind of sort of that, you can't have correct result all the time. You can have a chance that it will be correct result most of the time, sometime. And so even without dramatically simplified version how we can solve the task, it's still not possible to fully solve it. Yes, we cannot find all the computer science papers. We cannot define absolute popularity of all computer science papers because, well, we need to basically follow all the conversation across the world. Only Facebook can do that. And still, let's think about it. Like, if our whole data set is 1 petabyte of text data, well, just data, and downloading of that will take 1 week, weeks maybe, but building this information retrieval, data mining logic to get meaning from that, the whole data set will take ages. But what if instead we will just download 1 terabyte of that data, just one subset? It will take a few days, and then we will write small, very simple, with keywords, regular expression, data mining pipeline, which will be able to understand only 10% of it. And then we aggregate and get meaning from that data. How wrong result would be? Well, obviously it will be wrong because we haven't even seen the rest 99 gigaterabytes of data. But it wouldn't be exactly that dramatically wrong. If the data is randomly distributed across datasets, then most probably we will find at least that some papers are more popular than others. This is like, if you're a data scientist, you know it's actually coming from math statistics. It's called sampling. So we took a sample from the whole data set and analyzed that. So sampling is quite a big topic, but it allows us to have good enough results. Second problem, we have a bit of scale. There is always something doesn't work. It's like, I don't even remember a single day when everything was just fine. Everything is crashing all the time. There is always problem, some bottleneck, something is crashing, and there are a few reasons because of that. Beside that, very common, it's because of different resource limits. Like, think about, for example, memory leak. I don't mean memory leaks like in C++. No one, well, few people are using that. But think about memory leaks, which is like you're using some library, it's using some dictionaries for some caching stuff, and it has a reference to your object, and it has a reference to other objects, and now suddenly garbage collector cannot collect the data, and your memory goes up and up. And let's imagine we have 1 kilobyte leaked whenever we do one request. It's not a big deal, but when you have 100 requests per second, it's 350 megabytes in an hour. By the end of the day, in 24 hours, it will be 8.5 gigs of RAM leaked. Most probably it will be out of memory exception by then. And the same applies to disk space. If you have create temporary file, some of your library creates temporary file, and it's not removed at the end, eventually it will fill all your disk space. That happens because of amount of data. It's not exactly big data, by no means, but there's still some. For example, a few days ago, we built a lot of aggregates for every links, and I just run quite common job to recalculate all the aggregates. I did it 50 times already, and everything was fine. I ran it, nothing happened. I ran it again, nothing happened. Only then to realize that I had 2 millions of items to be reprocessed, and processing one item took 200 milliseconds. It's never been a problem before. 200 milliseconds is quite a lot, so I didn't even bother to optimize it before. I optimized it, I made it 20 milliseconds. It was 110 hours before, now it's 10 hours. So, yeah, it's one-threaded application, so some parallelism is needed. Even if I will make Wonder and make processing one items to 2 milliseconds, it's still 1 hour, more than 1 hour. So data is kind of add up. And there is also a third case. Third reason for all the crashes is we get the data from Twitter. And as I said, we have quite a lot of filters and a lot of false positives. And sometimes, because we have no control on Twitter, we have a load spike. And usually whenever we saw a tweet about paper, we extract the paper, computer science paper IDs, and we go to our database, extract all the tweets that we know about this paper, and build some aggregates. We find the most useful tweet about the paper, who is author, like all these kind of different aggregates. But we do it for every tweet. So basically, if there are already 2,000 tweets that we know about, and then there's 2,000 first coming, then from database we will read all the existing tweets, 2,000. And it's a bit of extra reprocessing, so it could be optimized, but it's for simplicity, and again, it's never been a problem. And usually when the cool paper or new paper get appeared, we find maybe 2,000 tweets about this paper, until one day that paper got appeared. So, as you can see, guys from Samsung implemented machine learning AI stuff, which allows you to have talking head, but it could even work from only one shot, one photo as an input. This is amazing, of course, but it's scary, and people get scared. And for that paper, we found maybe 60,000 of tweets that people are talking about that people went insane. All our processing pipeline basically crashed. The reason for that is because basically this paper is 30 times more popular comparing to all the papers that to the usual papers. So the logic of rebuilding aggregates executes 30 times more often. But the actual step of rebuilding aggregates is 30 times longer, 30 times more compute power is needed, because every time we fetch all the existing papers. So 30 times more often, 30 times more complex. And it's all about multiplication. So that paper generated like 900 more pressure to our processing pipeline than anything else. And then things crashed because of garbage collector, out of memory, and all that stuff. That things that I mentioned, all those issues, you cannot prevent it. I mean, I tried. Whenever I'm doing this e-com stuff and like all the things, every time, like production should be stable as hell. If it's down, I'm embarrassed. It's shame on me. But here, it's like I don't even remember a single day when everything were working just fine. There is no need to fight with that. You just accept that. Yes, it will be like that. And rather than fight with that, let's think about a workaround. But how we usually maintain quality in our project? So we do everything to prevent error from happening. So we do unit test, type system, integration test, pull request, code review. All that stuff is all about error prevention, but it's not enough. I mean, test coverage in all those projects is like 80%, so I have integration tests and what's not. But it's still happening. So instead of concentrating on error prevention, we should do error recovery. Error recovery is basically you accept that thing will go wrong, and it actually will go wrong. It's never a question if, but rather when. And after a certain scale, it's a question how often. And we should concentrate on error recovery. And the first thing, of course, is separation. If you have a monolith, then you have no second chance. If monolith is down, everything is down. That's the whole purpose of monolith, that it's one. Use microservices, it's the way to go. Then isolation is, of course. So we have maybe 15 different microservices and maybe 20 different databases. Nothing is shared between those microservices because one crazy microservice, if, for example, you're using like Postgres and all the services are using the same Postgres database, well, one crazy consumer could just like start to write a lot of stuff, or something will happen, and the whole server will go down. Isolation is the way to go. So every microservice has their own database. We're using RocksDB, is the local database, really nice one. And this is exactly the place where Kubernetes really shines. Because on Kubernetes, you can define limits on CPU limits, how much CPU can one service consume. And if it goes crazy, it will hit this limit and wouldn't affect the others. Most importantly, memory. Because memory is the most it's a limited resource, and when you hit it, everything will crash. With CPU, if you hit it, things will go slow, but nothing will happen. And with Kubernetes, we're using persistent disks, and with Kubernetes, you can allocate dedicated persistent disk per service, per container, basically. And yeah, this is the way to go. And also we have microservices, but how many HTTP calls between microservices we have? We have 0. We don't use, well, what is called, I guess, request response, or someone is using the like pool model when all the data is pooled. So there is a customer service, there is a front end calls the customer service and pulls the data. We don't use it. So everything is event driven. Everything is going through events. So all the microservices subscribe to events, they process it, and when something happens, they would like to inform the world about something, they just create a new event. We're using Kafka. It's really nice. But the last issue, it's also, regardless how much effort I put, regardless how much stuff I've done before, I only learn from production. So whenever I have some vision in my head about how things work, about performance, about how tools behave, how language will behave, how database query, regardless of how much testing I do before like putting anything live, production proves that I have a wrong vision in my head. And this is also given. This is like, I tried to fight with it, but it didn't work. Like test environment, all this stuff, it doesn't work. You have to accept that. And if you need to accept that, then, well, okay, let's do everything in production. So continuous delivery is the way to go. And rather than implementing a feature from beginning till the end, the development process is more like you make a deployment to production to verify each step that you do towards the goal, to ensure that everything that you do, that all the tools works properly. So example could be, maybe a couple of weeks ago, I started to work on a new crawler, and this is kind of specialized crawler. It needs to process maybe 300,000 of hosts per hour. But crawling is kind of simple things. It's like I've done many crawlers already, and implementing actually crawling the network stuff is like a couple of days for me. But we crawl not for the purpose of crawling, but to do something with data. And this is where data information retrieval, data mining logic has to be implemented, and that could take months. So the wrong way that ignores completely that issue is like go and develop something for 2 months and then put it live. This is wrong because we miss an opportunity to learn from the production. So the right way would be to create empty project, just health check, nothing else, Kubernetes definition, put it live. The next day, implement network level. Implement that it's crawl the internet, all those hosts, takes an HTML and ignores the output. It simply doesn't do anything with it, and put it live. This is useless. It kind of doesn't produce any value, but the value is that we start to learn how it works. What about network level? What about CPU consumption? How much memory it consumes? What about our logic? And then on the second day, it could be that you put this data and put it in a Kafka. But retention could be only 5 minutes. So after 5 minutes in Kafka, you don't even read it. It will be just removed. And this is a point where we start testing how our capacity planning, how much data is consumed, what about Kafka load, how much data we can put on top of it. And by the end of data mining pipeline development in 2 months, most probably we will learn so much already from the existing code, how it behaves in production. Maybe there would be already multiple petabytes that went through the whole stack, and most probably it will crash many times. But here we can make mistakes because nothing is it's not yet production. So we can do mistake and we can learn from production. Few things about Go itself. The whole project started with Kotlin JVM, and I love Kotlin JVM. It's really good language. But in the middle, when we have maybe 7 services, 1 crawler already implemented, I decided to try Go. I've been a long hater of Go, but I decided to try. And now, basically, everything, all the new services and all the existing services, I rewrote it to Go because of few reasons. So it's not going to be introduction to Go, but few main reasons for me. Well, first of all, it allows scale. And scale, it's in terms of overall performance, but for my use case, it was about memory. So previously I was using Kotlin, Spring Boot, and if you just implement health check and nothing and just put it live, it will consume like 100 megabytes. It's not a big deal if you have 1 service. If you have 15, you just throwing it away. It's not a problem, again, if you have unlimited pocket, but I have another needs for those gigabytes of memory. And with Go, if you create simple HTTP and with just health check, it will consume 5 megabytes, not 15, not 50, 5. It's like, I don't even remember when the last time I've seen the process that consumes 1 digit of memory. It's really nice. And in terms of overall performance, well, I'm not sure. Comparing to Java, maybe it's the same, but in terms of memory consumption, it's much easier. And it also makes it much easier to predict memory consumption. So I can just sit there and calculate how much request per second I send, what is the biggest, what's the average size, and just compare it. With Java, it's much, well, maybe I'm not that good with Java, but for me it was really difficult to estimate RAM consumption for Java application. Now it's actually better because now you can use Graal, VM, and there is even frameworks which are well suited for those kind of stuff. Second thing is Go Profiler. This is maybe not a surprise. Go Profiler, basically every language has a profiler, but with Go there are a few things. Well, first of all, it's part of a standard library. You don't need to install anything. It just, in order to enable for a service, it's like 1, maybe 2 lines. But most importantly, that profiler almost generates no overhead. So it's fine to have it running in production all the time. And this is lifesaver. I don't even remember how many times I saw a spike or saw something, memory consumption went through the roof, and I can just connect to production and just follow that, okay, well, this is about CPU consumption, but you can get the same for how much memory allocated, how much memory is used. So this is really cool for observability. You can get to the line level, and there is no those things like source map, debug builds. It just works, and it's really awesome. It helps us to find with performance problems, any kind of performance. It's really nice. And the last one is quality. Go has a type system, yeah, but it's actually more about testing. So although that I said error recovery is important compared to error prevention, but only after tests. Code is simply incomplete when there is no tests. And for example, the thing that I like the most about the Go is that if, for example, you have parser.go, then the test would go parser_test.go. So it will be placed in the same folder. So because test is a part of the code. Code is not complete without test. It's not like in Java when you have 50 folders up and then 50 folders down to find test for this model. And Go type system is, well, not exactly the best one, but it's good thing about that it's more, I guess it's quite similar to TypeScript with structural typing. So usually there is no need to define, like in Java, huge interface before you go to implementation, so you can mock stuff and do something with that. At the very first project, when I started to use Go, I just it felt so naturally, so seamless to write tests in Go that I didn't even try it, but I accomplished 80% of coverage. So it was really good. And also Go supports, test is, by the way, part of the standard library as well. And it supports like coverage report, and it also supports performance test. So it executes your code multiple times, and it gives you a report about allocation, about CPU, about iteration time. And this is also like really nice for any kind of performance related code. The best thing about computer science paper is that at the end, there is always a list of references. The things that I told you about is opposite of computer science, but here's the reference list anyway. Yeah, so the thing that I've done, this project was, first of all, is really nice exercise of how to operate a project like that. What are the good things? What are the challenges? How to solve it? Which tools scales and which maybe not? But most importantly, it was example of how to get meaning from data, knowledge from data without understanding the data, without being capable to understand the data itself by just using knowledge of a crowd. And this technique could be applied to any data set, any domain. And this is cool. Thank you.
Thank you. Hey, really interesting topic. It seems like a lot of the problems you solved are related to the specific service or the specific like data mining thing. Could you tell a bit about the service that you were actually building and like how these problems were faced that I didn't really get in the beginning? Like what is the thing that you were producing except for finding a lot of papers?
I didn't want to make it like more like advertising of a project that I've done. It was more about the way how it works. But basically, it's called Hot Computer Science, and the website and Twitter, but basically what we do, we just find the most popular paper, computer science paper every day, and then we publish that.
My question is that if it wasn't for the CPU and memory improvements that Go offered over the JVM, let's say, for example, there was a Kotlin-style language that did have the same kind of memory footprint and processing footprint as Go, would you be using that instead? Or have you been a Go convert now?
Which language do you mean, Rust? Well,
I mean, yeah, Rust would be an option, right? But
with Go, basically, there was the reason why I ignored Go for so long, that basically they had to reinvent everything. They had to reinvent all the libraries, all the drivers. Like you can, all the libraries had to be created. But nowadays, Go is kind of becoming mainstream, or maybe mainstream already. With Rust, unfortunately, they don't, I guess, still have any answer for HTTP async server, and it's more like cool geeky stuff, while Go is in production already in many systems.